Welcome everybody. It's a great pleasure to have here today Roy Maartens, who kindly accepted our invitation. Since 2011, Roy has held a national SKA research chair at the University of Western Cape in South Africa, which supports a team of students and postdocs working on cosmology. Before that, he was at the University of Portsmouth in the UK, and in 2002, Roy was the founding director of the Institute of Cosmology and Gravitation, which became one of the top cosmology research groups in the UK. Before Portsmouth, he was a lecturer at Wits University in South Africa. Roy was awarded a National Senior Research Fellowship by the UK Particle Physics and Astronomy Research Council and is a fellow of the International Society for General Relativity and Gravitation. Today, Roy will present Testing the Cosmological Principle, a new cosmic tension. Roy, you can start please when you're ready.
Thank you, Eleonora, and thank you for the invitation to your interesting and exciting CosmoVerse seminars on tensions and anomalies. I think we're all familiar with the most famous tension, which is the tension between low and high redshift measurements of the Hubble constant. Today, I want to speak about another possible tension, which, if confirmed, would have major implications for the standard model of cosmology. So my discussion is partly about confirming this tension, but first I need to describe it. This tension arises when we test the cosmological principle which underlies the standard model of cosmology. Well, what is the cosmological principle? It states that the universe is statistically isotropic and homogeneous. And on this basis, we can use the perturbed lambda CDM Friedmann-Robertson-Lemaitre-Walker universe as a model for cosmology. And that's absolutely fundamental to what we do in cosmology. The key consequence of the cosmological principle, which I will focus on, is that it implies that there is a unique frame in the universe. Equivalently, a unique four-velocity field, UA. And in that frame, or with observers with the four-velocity UA, average isotropy and homogeneity can be measured. So all of these fundamental observers moving with the radiation and the matter will see isotropy and homogeneity. And any observer with a different four-velocity will not see isotropy and homogeneity. So this sounds all straightforward, and it's part of the standard nature of the lambda CDM model of cosmology. So how do we test this? Well, the problem with testing foundations of the standard model is that to do the best kind of test would be not to assume the standard model and to make the test in the most general context. However, we have a problem that it's very difficult to do that in the case of testing the cosmological principle. So what we do is apply a consistency test. We assume that the cosmological principle holds, and we use a perturbed Friedmann-Lemaitre-Robertson-Walker model in order to apply a consistency test. And one of the most important tests of the cosmological principle is based on the fact that it requires isotropy in radiation and matter to be consistent. We can't have separate kinds of isotropy in the radiation, i.e. the CMB, and in the large-scale structure. This test was first proposed in 1984 by Ellison Baldwin in a famous paper, although not much read because it's not a topic that's received as much attention as it deserves. Well, what's the idea here? Heliocentric or solar system observers are moving relative to the rest frame of the CMB, and we know this from the Planck experiment. We measured very accurately our relative velocity relative to the CMB frame. The CMB frame is simply the frame in which the dipole vanishes. Right. Now, since we are not moving in the CMB frame. We are not at rest relative to the CMB frame. We're heliocentric observers. We do observe a dipole in the CMB. In the forward direction of this dipole, which is given by our relative velocity vector relative to the CMB frame, we see that the CMB is slightly hotter, and in the reverse direction, it's slightly cooler. And there's quite a simple expression for that. The temperature of the CMB for the heliocentric observer with the tilde is given by the CMB temperature plus a correction, which is the radial component of the relative velocity, n dot v naught. So when the n dot v naught is 0 in the equatorial plane, you see no difference. In the forward direction, n dot v naught has its maximum value. In the backward direction, it has its minimum value. So that accounts for the picture that we see on this slide. And this I'm writing down at first order in perturbations. So everything I do in this talk is at first order in perturbations. If the universe is isotropic about us, then the galaxy rest frame must be equal to the CMB rest frame. This is the Ellis-Baldwin test. So when we extract our relative velocity from the large-scale structure maps, it must coincide with the relative velocity in the CMB maps. And the same dipole needs to be seen. The difference is that in the large-scale structure case, instead of seeing hotter and cooler, we'll see more galaxies in the forward direction and less galaxies in the reverse direction. It's a very small effect, but it's larger than the perturbations, just like in the case in the CMB. So the simple formula was proposed by Ellis and Baldwin, and I'll be coming back to this formula later on, but their formula said that the number over density of this is the projected two-dimensional number density on the sky. For the moving observer, the number density contrast is corrected by a factor proportional to n dot v naught, just like for the CMB. But instead of having a 1, there's 2 plus x times 1 plus alpha, where x and alpha are two astrophysical constants, which I'll come back to later. In order to apply this test, since it's a 1% effect, you can imagine that you need a lot of galaxies in large sky areas. The dipole is the largest scale feature that we can measure in large-scale structure or in the CMB. So naturally, one thinks of large sky areas and high number densities. Early tests with the NVSS radio continuum survey, starting in 2002 and continuing up to even today, I've just given you a selection of references there. They generally came up with similar results, which are summarized in two facts. First of all, very importantly, the dipole direction from the NVSS was roughly in agreement with that of the CMB. The errors were large because the NVSS is a survey with not exceptionally high number density, but nevertheless, there was no challenge to the alignment of the dipole with the CMB. However, the speed, the relative speed that was extracted from that dipole was significantly larger than the speed that is accurately measured by Planck for the CMB. And of course, if that turns out to be true, that those speeds are not equal, this would break the cosmological principle. So this is the situation that existed, and I think many workers in the field believed that the data was not good enough for a reliable test. So this was kind of known, but not worried about too much. But then an improved test was applied by Sekrest et al. In 2021 and 2022. Instead of using the NVSS radio continuum survey, they used the CatWise 2020 quasar sample in the mid-infrared with 1.36 million quasars. So this was, you can see the comparison between the sky maps of the NVSS above and the CatWise sample below. Quite clearly higher number densities, and this sample could deliver a more robust and a more effective test for smaller errors. So Sekrest et al. Used the Ellis-Baldwin formula, and they concluded that the dipole magnitude is in tension with the CMB at more than 4 sigma. They agreed that the dipole direction was consistent with that of the CMB, but in other words, they were reinforcing the earlier results with a higher level of confidence given the better quality of the data. So we could say this is the most convincing evidence to date of a possible violation of the cosmological principle. If this is confirmed, if this is a true violation, it will be a major new cosmic tension. Very difficult to see a way out of such a tension. Similarly with the Hubble tension, it's very difficult to see a way out of the Hubble tension. This one may be even worse, who knows, if it's verified. But my claim is that this has not yet been verified. There are a number of tests that remain to be done before we can make a robust conclusion about this test. And the tests that one needs to make are both observational and theoretical. I'm going to be speaking only about the theoretical test. I'll just mention the observational issues because I'm not an observer, but there are many crucial observational issues involved as well. Many of them were taken care of by Sekrest et al., but not everything has been taken care of. And as observers know, systematics in observations, especially on very large scales, are very difficult to deal with. So these things have to be gone into before we can make a conclusion. On the observational front, the key problem with a dipole measurement, as I've said, is that systematics on the largest scales, particularly those on the larger scales, are very difficult to deal with. I won't go into details, but there are a number of such systematics, and not all of them perhaps have been fully investigated, and they need to be thoroughly investigated. Secondly, the second systematic is that in order to measure the large-scale structure dipole, we have to measure it against a far enough background to avoid nonlinear contamination by local nonlinear structure formation. The fact that we're falling towards the great attractor, for example, we have to go to higher redshifts in order to remove that nonlinear contamination. Because our theory is linear, we don't have a theory that will deal with those nonlinear dipoles. We could do in-body simulations, but that would be very complicated. So we rather exclude low redshift sources. So if we consider the future 20,000 square degree radio continuum survey planned for the SKA, which will be like a deluxe version of the NVSS, we have millions of radio continuum sources going out to redshifts of 6, almost 6. And you can see the median redshift there is above a redshift of 1, so we can happily exclude low redshift sources and thus exclude nonlinear contamination in order to perform this test robustly. The way to exclude these, because radio continuum surveys don't give redshifts, we would have to exclude the low redshift sources using cross correlations or matching with photometric and spectroscopic galaxy surveys. So simulations can be done to show the performance, the expected performance of the SKA, and the level of the noise is much lower than the NVSS, and the determination of the dipole is clearly going to be done with much greater confidence. In this simulation here, I show all galaxies in red and galaxies with redshifts greater than 0.5 in blue, and the white dot that you see there is the CMB dipole, which is fed into the simulations, and we can see that we can recover that very accurately, especially if we exclude the low redshift sources. If we don't exclude them, we have a much bigger scatter in the predicted dipoles. Okay, so that's as much as I'll be saying about observational systematics. I now want to turn to a theoretical systematic. Now, there are two aspects to testing this matter radiation consistency, as I mentioned. Let me remind you of that. The first, the dipole direction. It's important to notice that this determination is independent of theory. We don't need any theory to pick up the direction of the dipole. All we do is count galaxies. I mean, I'm not saying that's the best way to do it, but we can do it that way. We can simply divide the sky up into two hemispheres in a random number of thousands of ways, different ways, and then by that method find the maximum difference between forward and backward galaxy counts, and then we can determine the direction of the dipole. No theory is needed for that. The dipole magnitude is another thing. Here we need a theory to extract the relative speed from the dipole. That we cannot do without a theory. So of course you need the basic theory of the Lorentz boost, which is what we apply in the CMB. In the case of the CMB is very simple, and that formula is very accurate. But in the case of large-scale structure, the dipole amplitude is more complicated, significantly more complicated. So I'm just repeating this formula here, but now in the specifying the fact that the actual dipole that we're talking about is redshift dependent. So the number density contrast for the moving observer is the stationary number density contrast, the one who's at rest relative to the CMB, or relative to the matter rather, plus a dipole correction at each redshift, which I'm calling D3 just to emphasize that it's three-dimensional. And the amplitude of this dipole correction is D3 times V naught. So we need the theory to tell us what D3 is, and then the measurement tells us D3 times V naught, so we can extract the relative velocity V naught. This is a simple but critical point to make. And D3, because it depends on redshift, and current observations have been using 2D projections on the sky, we also need to take the next step after we've derived D3 to project that onto the two-dimensional sky. So all of the measurements that have been done up to now have used the two-dimensional number counts with the two-dimensional projection D without a subscript 3. So that's what I'm going to be talking about from now on. The Ellis-Baldwin model for the two-dimensional dipole, I'll remind you, is 2 plus x times 1 plus alpha. Remember, the corresponding value for the CMB was just a 1. dCMB equals 1, but in this case, DEB, or Ellis-Baldwin, is 2 plus x into 1 plus alpha. X is basically the magnification bias of the galaxies, and alpha is the spectral index of the galaxies. And it's clear that the Ellis-Baldwin formula assumes that both of those are constants. X and alpha are constant. Now, observations, as I've mentioned, measure the dipole regardless of theory. So if we think about the true theory, we've got d times the velocity of galaxies on the left. That's the magnitude of the dipole. And on the right, that should be equal to the theoretical value, if Ellis-Baldwin is correct, times the velocity of galaxies. But what observers have found using the Ellis-Baldwin formula is that the velocity of galaxies using Ellis-Baldwin is greater than the velocity of the CMB. Now, before we go further, I should just say that in principle, you should be able to see that it's possible that the CP is not broken. In other words, the cosmological principle does hold so that the galaxy speed is equal to the CMB, but that the Ellis-Baldwin formula is incorrect. So in that case, if in fact the cosmological principle holds and V naught galaxies is equal to V naught CMB, then that will be because the Ellis-Baldwin dipole factor D is less than the true dipole factor. And that's the point that I'm making, the crux of the point that I'm making. This means that we have to check the Ellis-Baldwin formula by performing the correct two-dimensional projection. In the original Ellis Baldwin paper, no projection mechanism was proposed. The formula was simply derived without reference to any radial projection. So that's a gap which has been filled subsequently and which leads to the rest of what I'm going to say. So in order to make that clearer, let me return to the redshift-dependent dipole, the D3 that I was talking about. We're thinking again of the heliocentric or boosted observer with a 4-velocity U tilde relative to the CMB rest frame, which is our reference. Remember, we assume the cosmological principle and then we derive the theory on that basis. So to first order, U tilde is equal to U plus V, where V is the relative velocity. Now, these galaxy redshift surveys are either spectroscopic or photometric. The observer, the moving observer, counts the number of galaxies in a solid angle in a given direction in a given redshift bin. That's the observed number density, where little n is the unit vector of observation. D omega n is the solid angle about that direction, and dz is the redshift interval in which the galaxies are being counted. Because the observer is Lorentz boosted, she or he measures a different redshift and direction. There's aberration and a Doppler boost involved here. And then if we apply that, using the fact that the total number of particles is the same for the boosted observer and the CMB observer, so dn is either equal to the observed number density times dz d omega n in the CMB frame, or to the heliocentric observed number density times dz d omega, all in the heliocentric frame. So using this conservation of particle number, we can derive the fact that the boosted observed number density n tilde is the non-boosted n times a factor 1 plus 3 times n dot v naught. Very simple result. And what does it tell us? Well, it generates a dipole, as I said, of D3, where D3 is given by 3 plus d log n over d log 1 plus z. This is to be compared with the CMB, where D3 doesn't exist. We don't have to do a three-dimensional, we can't do a three-dimensional thing in the case of the CMB. But if you just compare with the D2 of the CMB of 1, you can see this is more complicated. And what you can also see from this formula is that the redshift distribution of the observed number density of galaxies is critical for deducing the dipole. Now we have to project this three-dimensional dipole onto the 2D sky, and we have to weight our projection. Our radial projection must be correctly weighted according to the redshift distribution of sources. So I've shown D, which is the two-dimensional dipole. It is a radial integral against redshift with a weighting factor f of z times the three-dimensional dipole that is shown above. And that weighting factor f is the observed number density n itself divided by the integral of that observed number density, which is the number per solid angle after you integrate out the redshift. So this is the critical formula that was not considered by Ellis Baldwin and has not been applied in the various tests that have been given in the literature. And this projection was studied by Dalang and Bonvin, and also in a more recent paper by myself and my collaborators, Gwendoline, Piat, and Clarkson. So let me just say something now in order to make contact with more familiar quantities. Up to now, I've been working with the observed number density curly n on the left of the first equation. but we typically also want to know things in terms of the physical number density, the co-moving number density, little n on the right-hand side of that first equation. And the relation between these two in the background is that curly n is the radial co-moving distance squared over 1 plus z times the co-moving Hubble parameter, all multiplying the physical number density n. And what about the physical number density n itself? Well, it is just the integral over magnitude of the luminosity function phi. So this is how we start to make contact with observational quantities, well, sorry, with observer quantities. So if I feed this information into the formula for D3, the three-dimensional dipole magnitude, we find a factor 2 plus a Hubble rate, two Hubble rate terms, where the cosmology comes into the dipole, h dot over h squared plus 2 over rh. And then a final two terms, which involve the magnification bias S and the evolution bias BE. So the magnification bias is familiar to most people. It's simply the partial derivative of the number density with respect to magnitude at the magnitude cut, roughly up to a factor. And the evolution bias, something which is less familiar, but this is simply the redshift derivative, the logarithmic redshift derivative of the number density at the magnitude cut. And BE gives us a measure of to what extent the number density of galaxies deviates from being conserved. For example, through mergers or through other evolutionary effects in the history of those galaxies that we're observing. So by the way, the X from the Ellis-Baldwin formula is just 5 over 2 times the magnification bias. Now, when we project this three-dimensional dipole factor onto the sky, remember the Z integral has the weighting factor f of z, multiplying the three-dimensional d. If we go through that, we find 2 plus an integral of f of z times x of z times 1 plus alpha of z. This is what we would have in the Ellis-Baldwin formula if it had been derived from first principles. Alpha is a spectral index of the flux densities of the sources, but you can see that the original Ellis-Baldwin formula can only be recovered from the correct expression above if we assume that x and alpha are constant. Okay? And in reality, what we should be doing is extracting x and alpha from the luminosity function. Instead of assuming that they are constant, we should be extracting them or equivalent quantities to them from the luminosity function. That would be the correct way to actually determine the theoretical expectation for the dipole magnitude. So we take an example of the EBOS quasar luminosity function studied by Wang et al. In 2020 and others before them. We find that for x of z over the redshift range from just below 1 to about 4 is definitely not constant. And neither is alpha. If we extrapolate from the EBOS quasars to the Catwise 2020 sample, which is much bigger, then the tension with the CMB can in principle be removed, as shown by Dalang and Bonvin. They're not saying that it is removed, they're saying that the fact that you have to actually use redshift dependent quantities and integrate them out gives enough leeway for the tension to disappear. The fact that they couldn't actually make a specific test is that we can't just expand the EBOS sample to the Catwise without taking account of differences in selection criteria and other observational complications. So it's still an open question, but the question now has been posed correctly. We have to actually find ways to correct the Ellis-Baldwin formula and see what the resulting relative velocity is. Now, current models of the EBOS quasar luminosity function have enough leeway in them that if we choose 6 popular models in the literature, that each of which fits the data, the current data from EBOS, they produce dipoles that are up to 3 sigma in tension with each other, which is what we showed in our recent paper. So I'm just giving you a little sketch here showing the 6 models from the MCMCs that were performed, showing the errors and the best fit dipoles from these 6 different models. And you can see it's possible, each of these models agrees with the data within current errors, and yet they can produce a velocity which is in tension up to a level of 3 sigma. So this does just simply illustrate that it is possible that the tension can be removed by a correction to the Ellis-Baldwin formula. We're not saying that the tension has been removed. It remains to actually pursue what we're advocating, which is to extract the information from the luminosity function. And that is not an easy thing to do. And we're busy talking to observers about it, and I think other observers are thinking about it, but this is not a test that is easy to perform, and the current slide actually shows that, because small deviations in the luminosity function models can lead to large consequences for the dipole. And the data is simply not good enough to make this distinction more tight, smaller. So in summary, I'm sorry if I've gone too fast. Seems I've got to the end quickly, but that will leave more time for discussion. My summary is the following. The first statement is that the simplified Ellis-Baldwin model means that in principle, the apparent excess velocity which follows from this model could be due not to a new tension, but to the implicit approximation of constant magnification bias and spectral index. This point was first made by De Lange and Bornbaum. If we want a theory-robust dipole, we need a good model of the luminosity function, as shown in our recent paper. Now, I'm just reminding you of the key formulas at play here for the 2-dimensional dipole in terms of the underlying 3-dimensional dipole, the physical 3-dimensional dipole, which needs to be properly and physically projected along the redshift direction. So I'll stop there and happy to take questions.
Thank you. Thanks a lot for the very interesting talk. I think we have some questions already in the chat. I think George had some comments.
No, so it's okay. So I've had some answers from various people. Okay,
great. So, Erin?
Yeah, okay. Hey, Roy, thanks for the talk. When I first saw this cosmic dipole stuff, the studies, right, it was clear that basically you could attack both the radio galaxies like MVSS, TGSS, whatever, and the quasars on the common methodology. So there was a clear systematic you could go after and you could pull them apart. So you had to go beyond them. You have to go beyond the cosmic dipoles and you have to start building a science case that basically has other observables and you're pulling them in. So at the time I was aware that there was work by Kostas Mikas and that he was finding anomalies in scaling relations in cluster galaxies or galaxy clusters. They're basically tracking the CMB dipole direction and they shouldn't be doing that. And then we went after type 1a supernovae, which again are corrected to put them in CMB frame, and you find that H0 is higher in a particular direction in the sky that's consistent with, you know, the CMB dipole direction. And now I've done it with Pantheon Plus. I haven't put the paper out, but it looks like it's a 3 km/s per megaparsec discrepancy in the redshift range that SHOES has, right? Now you can do this in the flat lambda CDM model, or you could do it with cosmography. You just need H0 and another variable. Doesn't this seem to say that there really is a problem with the CMB frame and it's not just confined to, you know, quasars and radio galaxies and their dipoles? That's the question.
Do you have to take that as overtime, or can you take the additional?
So there's a bigger picture here, Roy, right?
Yes, sorry, I just hear someone else in the background, who I can't hear properly. That's an interesting question. I agree with you that all of these things should be pursued in parallel, and there should be cross-talking between them in terms of the people who are doing the different things. I fully agree with that. I haven't looked into the issues of bulk flows and dipoles from supernovae and from other sources, because
right. But it would be nice if your talk mentioned those things, right? Just to balance it up.
It would have been nice, yes.
Right, and the other thing as well, once you have an FLRW metric, H0 is a constant. It has to be a constant on the sky. This is a very simple way to go after FLRW or the cosmological principle. You may have to use a model, but again, if you do it at low enough redshifts, there's not much that can go wrong.
Yeah, look, one has to apply the tests of the cosmological principle from different directions. This is one of them. And I claim this is a key fundamental test. This test requires a high number of galaxies out to high redshifts.
Right. It could be messy, though. It looks like it's messy.
I think, when you're looking at supernovae, you've got low numbers, you've got just as bad systematics as you have for galaxy surveys. I don't think it's any better at all. And I don't think the supernovae, there's not enough supernovae to give a robust test of the matter dipole. They can do other things for you. You can talk about the Hubble constant.
Right, but are you happy to live in a, sorry, Roy, just let me ask this question. Are you happy to live in a universe where H0 is higher by 3 kilometers per second per megaparsec in one direction versus another, and still say that's an FLRW cosmology?
I'm happy to live in a universe where there's no definite answers to the physics questions that we pose, and that the answers that we come up with keep changing. Because
okay. Wait, thanks for the talk. Thanks for the discussion.
That's something natural to me.
Thank you. Shaheen?
Thank you, Roy, for the interesting talk. I have a more down-to-earth question. So you started with giving a definition of what the cosmological principle is, and you mentioned that statistically isotropic and homogeneous universe is but I was wondering what's the relation between this cosmological principle that you define and the FLRW cosmology. So are they synonymous to each other, or is there a difference?
So that's a good question. If we try to pose the cosmological principle in generality, we start running into some problems. We need to be able to define statistical isotropy and homogeneity. And if we can do that, then we need to show that a perturbed Robertson-Walker model somehow naturally arises from almost isotropic and almost homogeneous. And these are subtle questions, and the reason, the basic and fundamental reason that they're subtle is that we don't know how to average in general relativity. That's the sort of dirty secret of our craft. It's a bit like people doing statistical mechanics and then averaging it and doing thermodynamics, and that works wonderfully because you can actually properly and without ambiguity, you can do your averages over statistical physics and arrive at thermodynamics. You can't do the same in gravity because gravity is a nonlinear field theory. So everything we do in cosmology, I think, has to be with the proviso that we are just assuming that when we do average in our observations, that corresponds to some kind of physical average in reality within Einstein's theory in the universe that we observe. And that assumption, unlike the case in statistical mechanics, is not something that we know how to test because we do not know how covariantly to average in general relativity. But we make a reasonableness assumption that although it's not clear how we technically should do this, that the averaging that we do in our observations on the scales that we measure and the scales that we're concerned with reasonably is expected to correspond to an average of Einstein's field equations. This is I think the issue that you're pointing to.
And maybe in making this averaging, there's also a scale coming in, right?
Also,
some scale coming in. For example, if we are beyond some scale, we may.
yes, precisely. For example, we treat cold dark matter as cold, and we treat the halos as moving like particles on geodesics in space-time. But in reality, in order to model galaxies as part of a pressure-free fluid, we have to go out, we have to average on large enough scales so that we're not dealing with small-scale nonlinearities and things which actually mean that the dust model starts to break down when there's stream crossing. So, of course, that scale, we're not sure exactly what it is, but roughly speaking, we have an idea of reasonable scales that we can average on. The four velocities that I talk about and which define the dipole and all sorts of other things in cosmology, they all implicitly assume that there's an averaging scale below which your modeling, your perturbative modeling breaks down. And by the way, n-body simulations cannot solve this problem of averaging Einstein's equations either. By definition, they bypass the averaging problem.
Right. So maybe then one should look for a better, more operational definition of the CP. I don't know.
Yeah, I think that's a good idea, but people have done this, and there's also related to this is the so-called fitting problem. Since we don't know how to average, which particular FLRW background should we attach to the real universe? So we don't have a clear way of, Owen would like this because you could have different FLRW models with different Hubble constants, which could
right. But sorry, Roy, if I can just jump in there, right, before you get there. If you just use cosmography, what's the difference, right, at low Z?
Well, cosmography doesn't get around the averaging problem.
But the fitting problem it will get around, right? So there is no fitting problem.
Well, if
there's an averaging problem, is that it?
If you do away with the Robertson-Walker background, yes, then you've done away with it. Then there's not a fitting problem.
Right. So just to put this in perspective, Adam has shown that basically no matter which cosmological model you use at low Z, you basically get H0 to be 73 or 72. So it's what we expect. The cosmology is irrelevant, right?
Yes, but there's all the averaging issues don't go away, and that especially at low Z. The averaging problem is worst at low Z.
I agree there's an averaging problem. Just the fitting problem may not exist.
Okay, fair enough.
I think we can go ahead. Mary Noher?
Yes. Hi, Roy. I'm always happy to hear a discussion of the cosmological principle considered seriously. And as an alternative to the theory you could use, I'm happy with the exact models. And in fact, in the quasi-spherical Secular solutions, that the distribution of the mass over each single sphere has a form of a mass dipole superposed on a monopole, which can be removed somehow. Do you think this could help you in your test of the cosmological constants? I know that the fitting is not easy, but what's your opinion?
Yes, I think in principle it's something to look into. It reminds me, for example, of Swiss cheese type models, which are deviations from standard Robertson-Walker, which have been used to test the effect of structure on light ray propagation. And I think those are valuable things to do, but people have also looked at Zechari's models for the behavior of light rays in response to traveling through large-scale structure, because it's something that can be done almost analytically, certainly without n-body simulations. And I think those are valuable. I hadn't thought about testing the cosmological principle with such models. Either one tests a fundamental principle like that in a general space-time, or in a perturbed Robertson-Walker. I'm not clear how one could use, say, the Zekarej models as a consistency test. What might be more to the point is that if it turns out that there is a real tension in this dipole, that in fact matter is moving relative to the CMB, then one wants to look at models in GR, solutions in GR, which can have that kind of property, like some of the Bianchi models, for example. People have started looking at that.
Yes, I agree, because the fitting with the observations is not easy. That's true.
I agree, and it's not clear what will happen if we have to abandon Friedman-Robertson-Walker. I don't think we're there yet. I don't think we're close to that yet. But if we get there, well, we're going to have to deal with it. But for now, the tests must be pursued and improved upon. I think that's
yes,
what we are.
Of course, it's a very important test. Yes, I agree. Thank you.
Thanks, Marianne.
Thank you. Nikolai?
Hello, Roy. Thank you
Hi.
very much for a very interesting talk on a very interesting topic. I have a simple question. Has anybody tried to find higher order multiples in this quasar distribution functions? Because finding a quadruple, I suppose it's even harder than finding a dipole, but that would be even more disastrous for the cosmological principle, because that's something you cannot cure by boosting your reference frame. So has anybody looked at that?
Yeah, that's a very good question. It's as far as I know, the Sekrest et al. Did look at the quadrupole. One can look at the quadrupole as, for example, using heel picks. You can get heel picks to generate the angular power spectrum for you, and you can check the different multipoles. So it's not that it's impossible to do. The same kind of systematics that affect the dipole will affect the quadrupole, because it's on very large scales. The point would be that if you find there's a very large quadrupole of similar magnitude to your dipole, then the first conclusion you would make, or the first guess you would make, is that your data is suffering from systematics. And if you convince yourself that those systematics don't exist, then you've got a bigger problem, as you say, and you've got a deviation from a Robertson-Walker background, which is more difficult to fix than if it were just a dipole.
Okay, thank you very much. I think the primary issue would be first to try to estimate how big of a dipole an FLW model can actually tolerate. And then, of course, think about the systematics, which will be probably even harder. But it seems like an interesting direction of research. Thanks.
Yeah, thanks.
Thank you. Jenny?
Hi, Roy. Thanks for the great talk. I would
Thank
have a question about finite infinities, because on the equation here on the slide, you integrate over all redshifts from 0 to infinity, but your observables have only a finite redshift. So should you take this into account in your model, and would this change your conclusions?
It wouldn't change the conclusions, because in a sense, this is just a shorthand. We basically, there's a window function which I could add to the weighting function f, which simply kills the signal where there are no galaxies.
Yes, right.
So, and also, as I mentioned, we should start above the lowest redshift, so it doesn't start at 0 really.
Yes.
It should start with maybe 0.1 at least, and if not bigger. And going out to infinity, well, you just go to where you cut off the number of galaxies. So it's going to be a finite integral. There's just a bit of a lazy shorthand that.
Okay, so you already took this into account in your modeling, actually.
Yes, yes, that's taken into account.
Okay, thanks a lot.
Thank you. George?
Yeah. So Roy, when you derived expressions using the galaxy luminosity function,
Right.
I think that, I mean, if you really want to be rigorous about it, then you have to have something more than that, because it depends on how magnitudes are measured, whether they're isofocal magnitudes, whether they're extrapolated magnitudes, and you'd need to know something about the distribution of profiles, surface brightnesses, and so on, and have a multivariate function, not just a luminosity function. And you need to know how the magnitudes are measured.
I agree, and the number of complexities involved there is it's frightening, especially to me.
Yeah.
And I think we're thinking a lot about, but not without success so far, ways to try and simplify this. Samples that we could use, for example, that don't require such detailed knowledge of the luminosity function and the way in which it's measured. For example, if we think of 21 centimeter intensity mapping, it's much more simple from a luminosity function point of view, because it has the magnification bias is fixed to be exactly 0.4 because of the nature of intensity mapping. And the evolution bias depends purely on the average temperature. It's not specific to the survey. It's a universal quantity, unlike with galaxy samples. But the problem with 21 centimeter intensity mapping is that the radial long wavelength modes are lost to foregrounds, and those are exactly the ones we need for a dipole. So what seems to be the ideal sample for testing this cosmological principle this way actually has this problem of foreground contamination. But we're thinking of ways
you're never going to solve that problem.
Well, we're hoping that maybe some cross correlation might help us, or maybe there are other ways to do it. But yeah, I'm not optimistic about that.
You're fighting many orders of magnitude.
Yeah. So the CMB has the same problem of foregrounds, and that's been dealt with. And but the CMB is a much simpler thing than 21 centimeter.
But the foregrounds for the CMB are really easy.
Yeah,
they're really easy to deal with.
Yeah. But they weren't easy in the beginning, were they, George? It did take a decade or more.
Yeah, I mean, it depends on your frequency. Once you go to high frequencies, then it becomes a very simple, straightforward problem.
Yeah, I'm aware that the higher the
I mean, with Planck, people often say that the foregrounds are lowest at about 70 gigahertz, which is true. They're lowest in intensity at 70 gigahertz. But actually, the cleanest channel for Planck is 140 gigahertz, because then you go to high frequencies, the foregrounds are much simpler, so you can deal with them and get a much cleaner CMB map.
Sure. I mean, the problem with 21 centimeters is that the lower the frequency, the higher the redshift. So you want to go to high redshift, so foregrounds get worse.
Yeah.
It may be, George, that in the end, this test is not practical because we can't actually measure the luminosity function in any reliable way. And that would be a result in itself, but it would still, the questioning of the Ellis-Baldwin formula is not overturned by the fact that doing it correctly is very difficult. It may well be that Ellis and Baldwin have a good approximation, but we haven't yet been able to show that with any data set. So,
yeah, well, at least you would want to know, from a careful analysis, how good the result can be.
Yeah. I don't know if I'm being naive, but if observers could give me the number of galaxies counted per redshift bin per square degree and nothing else, then in a sense, I might be able to use my original formula here.
Yeah, yeah,
This one here.
yeah, yeah.
All I need is the observed numbers. That's it. Sounds too simple, but it's only when I start comparing this to the number density at the galaxies that I bring in the complication of magnification bias and evolution bias. But somehow one can't cheat that way. I'm sure that that's not going to work. But nevertheless, if observers could just give us tables of curly n, that might be helpful.
Can I make a comment on CMB now that George is here? George, are you still there?
Oh, yeah, yeah.
Right. So George, there's at least 2 papers in the literature where they take the Planck data and basically they mask half the sky and they fit the lambda CDM model, right? And then they rotate that in. There's one paper out of Hong Kong where they rotate it on 48 directions in the sky, and they find the largest variation in H0, which is roughly 10%. Again, assuming the lambda CDM model is in a direction that more or less coincides with the dipole of the hemispherical power asymmetry. Do you buy this result? Now that would say Planck has 1% errors, but then there's a 10% variation in H0.
Yeah, I'd be astonished if it were if that were true, but it's not something that I've looked at.
Okay, it's something we should look at, though, right? Somebody should look at.
Somebody should look at it because, as I said, I think it would be astonishing if it were true.
Thanks.
It's really difficult to do, right? You know, if you go to small patches of the sky.
So these are half sky masks, right?
Half sky.
Right, half sky masks. So it's a hemisphere split. It's very clean.
Okay.
And so 10%, but the coincidence is that it aligns with the dipole of the hemispherical power asymmetry, which we know is there, but cosmologists always say it's a 2 to 3 sigma fluctuation.
Right.
Now, if that result is true, then that absorbs Hubble tension. It just says, we really only understand H0 to about 10%. But obviously we have a problem with the lambda CDM model because the errors are too small. I'll send on the references.
Right.
All right.
Okay. Do we have any other questions for Roy or comments? No? Okay. So I think we can stop here. Thanks a lot again.
Thank you.